Good day everyone. Alright, so in this video I want to talk about gravitational potential energy, or at least in the framework or with relation to the Newton's law of gravity. Alright, so let's get into it. First things first that I want to do is I want to remind us all chapter 5. Alright, so chapter 5 we've learned a few things. Among others, we learn how to define work done, and this work done is defined to be F dot R, the dot product between force that creates the change in position, which is what we call displacement. So R is what we label displacement to be, and F is the force that changed the position. Another equation that you might have been familiar with is EGP, where EGP represents the gravitational potential energy. Okay, and this is usually the equation that we use mgh, where h is the height, right? Is the height of the object. And when we talk about height, we are talking about from the surface of the earth. All right? So we are talking about the surface of the earth. Now, fast forward into chapter 7, where we learn about Newton's law of gravity. Where Newton's law of gravity tells us that the force, the gravitational force, is equals to G m1 m2 over r squared. Okay, now these are very different equations because one talks about simply the height and the mass of the object, whereas the other one talks about the product of the masses of the interacting bodies and the distance between them, right? So now we ask the question, can we find an equation for the gravitational potential energy, right, as a function of the masses of the interacting bodies and the distance between them? Can we find that? Do we have that equation? Let's think about it, shall we? Let's consider, right, the Earth, a box on the Earth at position Ri, right? And then we lift that box up into a final position of Rf. We can change our reference so that this is 0 and this is R. Okay, so this is the final position and we call it R. Or in the old equation we use mgh, so this is the new, is just h. Okay, now in the, let's consider that the weight is moving downwards because it is, and then we know that the direction is going to be upwards, so this is going to be the direction of R. Okay, so we can calculate the work done to lift this box to be F dot R, right? So it's fairly simple, and it's in one of it has to be in a negative direction because they're opposite. Okay, but let's not worry about that yet. Now, um, Newton's law of gravity tells us that F equals to G m1 m2 over r squared. We can substitute this value into here, and what we will obtain is G m1 m2 over r. Okay, and following the work energy theorem, what we get is that this is the equation for the gravitational potential energy. Okay, but because they're in opposite direction, we can always just add a negative sign. Again, the negative sign simply here tells you the weight that is in the opposite direction from the weight. If we're talking about the work done by us to move the the box upwards, so that means our external force, right, is in the same direction as the displacement, then that negative sign goes away. So the negative sign simply tells you whether you're considering the Fg, which is weight, or the F external, which is the force that we put in. Okay, so because Fg is in the opposite direction of displacement, we have a negative sign. Okay, so all right, to summarize, right, we have worked out how we can produce or derive an equation for the gravitational potential energy as a function of the masses of the interacting bodies and the distance between them. All right. So that concludes our video today. Thank you very much, and I'll see you in the next video.